My colleague, Professor Darryl Holm, is going to talk about stochastic Lie transport.
Oh, thank you very much. Thanks for inviting me to come. I'm happy to be here to see friends, give a talk. And this talk is about stochastic Lie transport and metamorphosis. So a good part of the talk will be spent defining those terms. So let's just begin. So, why am I giving this talk? Right. So I'm like a way to predict the uncertainty and variability in the evolution of shape in ensembles of images of disease progression. Right. For example, so we have shapes which are changing with time, and they may be changing with time for some biological reason, which we may or may not know. Still, we would like to be able to track how things are changing, and we would like to have some sense of the variability in populations of how these things change, and we would like to have some sense of predicting the variability, or predicting the uncertainty. Actually, not long ago, a month or so ago, in August, my wife broke her leg, and right at the hip here. And just before she left, the doctor, and she did it in California, like the most convenient place to do this, right when I live in London. But just before we left, the doctor said there's a 50-50 chance that what she broke is the little stem that goes between the femur and the ball in the socket. Okay, and he said there's a 50-50 chance that before this gets mended, or when it's mended, the ball will have died. And then you'll be looking at a hip replacement. And then, maybe not even a week ago, I went out and bought champagne because the doctor, looking at the new x-rays, says, there's only a 10 or 15% chance that the ball will die. So when people look at these images, right, you'd like to be able to have some sort of sense of uncertainty, right? And so this is the kind of thing that maybe this method, metamorphosis, will help us to deal with this kind of problem. So how would we accomplish this? We like to, and today we're going to talk about an approach of modifying a method of image matching which is called metamorphosis to allow Lie transport along stochastic curves in the diffeomorphism group of the smooth invertible transformations. Okay, so in shape modeling and in shape analysis, there's a manifold of shapes, the diffeomorphisms act on them. We choose diffeomorphisms to look at it for the same reason that John Ball did about looking at materials. And generally we think of, with elasticity, for example, that we're talking about deterministic evolution. But the way we do it is we say, what is the action of these invertible maps on our material points? And we say, it's the action. Actually, this is the change of shape that we wanted. So we could just, instead of following the material points themselves, we could lift the motion up onto a curve depending on time in the diffeomorphism group. And then we can model the motion because we know that what the action of the diffeomorphism group is on our material. To make it stochastic then? To start introducing probability, to start introducing stochastic processes, all we have to do is make that time-dependent curve on the diffeomorphisms be a stochastic process. And it doesn't change the fact that they're diffeomorphisms. They're still smooth invertible maps. It's only the time evolution which is going to change by this approach. Okay, so that means that when you do analysis with this type of problem, you have smooth invertible maps working for you just like you had before. Okay, so it's an interesting feature. If you try applying this to fluid dynamics, you try applying it to the Euler equations in 3 dimensions, that famous problem, then when you have deterministic evolution of the Euler equations, you have 3 properties that you know. You have local in time existence, uniqueness, and you have this Biel-Cotto-Maida criterion for blow-up. That if it blows up, then this BKM criterion must be satisfied. And if you add stochasticity to the evolution this way, just by making the curve from the diffeomorphism group into a stochastic process, what you preserve about the analysis? You preserve local in time existence, uniqueness, and BKM. All 3. So this particular way of introducing this problem, these stochastic processes, is not interfering with the analysis. So that's just a point to make, that there's a commonality between them. So we're going to modify this method of image matching, which we'll discuss. We have to set it all up and talk about the notation and definition stuff. That's part of the talk. And then we'll introduce stochastic curves. And we will have made metamorphosis into a stochastic process, which we can run in again and again with different realizations, and try to learn something from the data about how to model the stochastic curves, because it's all going to be based on data for the stochasticity, and then the issue is going to be to find the evolution, okay, of the velocity, which is called the drift in a stochastic process, given that you know something about the stochasticity. Okay, so what are we going to get? We'll get stochastic PDEs for the evolution of an ensemble of shapes. Okay, and we'll discuss some of their properties and some of the outstanding challenges. And I've already mentioned one of the features, that a lot of the analysis, a lot of the analytical results that we know already from shape analysis are going to be preserved. There's a lot of geometric meaning going on and ingredients. And then it actually turns out that it's much more like fluid dynamics than we ever imagined. The forward evolution of for this metamorphosis turns out to be just in the same class as the forward evolution for complex fluids like liquid crystals. It's exactly the same framework. So the bridge, right? The bridge. Okay. So we're interested in variability in images. These are just some typical images, and if you look from one to the other, there's all kinds of differences, especially in fine structure, and it sort of reminds you of fluids, right? Images have different length scales, and fluid flows also have different length scales. And they also have shapes to the major components. So this is the point I want to make in this talk. There is an equation called EP-diff, which is going to have many variants, but it's basically a geometric equation, which I think is this big bridge between images and shape analysis and fluid dynamics. Okay, so let's try to develop some of these parallels between shape analysis and ideal fluid flows. We already heard earlier from John Ball a lot of parallels, very careful, detailed, definitely well-defined parallels with elasticity, and those parallels are, are right at the detailed microscopic level even. So here, and there are issues that come up in one field that can be transferred over to the other. Here I'm going to be generally talking about a fluid flow which is essentially continuous. So there won't be any tears in it, because you have to have an ability to invert this map. But it's just the same picture that John was talking about. These are the x's and these are John's y's, which I call little x. So we have a fluid domain, and in this picture here, the fluid domain is in R2. And we have some reference point in it. There's some diffeomorphic map that changes, that's part of the flow. And there's a velocity, which is the velocity of how this Lagrangian point moves as a function of which one it is. And it's being transferred onto the curve in the group by saying the current position of the fluid point that was originally at this point x is now that's mapped into it, the position x in space here, by this diffeomorphism. It depends on time. Okay, so the spatial velocity of this guy is just its time derivative, right? That's this relationship here. And if we want to go back from g dot of x back to x, we can just compose with the inverse. Okay, so now we know what this vector field here is in the spatial representation. Okay, so to just get going, we want to use Hamilton's principle, and we need a Lagrangian. So let's take our simplest case. And of course, we don't have to be restricting to 2 dimensions. This works in n dimensions. So if this is our Lagrangian, which is motion on the group. The reason we're interested in motion on the group is because always in the beginning for this game, is this game called geometric mechanics, you ask, what is, is this motion on some manifold associated with an action of a Lie group on this manifold? And when it is, you can do like I said, lift up the motion on the manifold onto motion on the Lie group and some curve acting on the manifold. And that's what we've done here. We now have g dot squared. We in Lagrangian coordinates, in Eulerian coordinates, we know it's g dot g inverse, mod squared. We choose a norm. It could just be L2 norm here. And that's the usual norm for Euler's equations. And then the theory states if you take this variation and use Hamilton's principle, in terms of V, you don't get actually the Euler-Lagrange equations. You get a set of equations called EP-diff, the Euler-Poincar equations on the diffeomorphisms that are equivalent to the Euler-Lagrange equations. And here they are. So it is partial time derivative of dl dv, which is a function, and since V is a vector field, this function is a one-form density. It's something dual to a vector field in pairing in L2. And L star acts on it, and for one-form densities, well, L star is the same as the Lie derivative, and the Lie derivative is the time derivative of the pullback of the whatever you're acting on, evaluated at the original time. So it's just a tangent. It's a tangent to the action of the group on this object. Okay, and having solved this, okay, then we assume that we, with our, did someone say something? No, oh, sorry. We assume that we can go from dl dv to v, so that this is invertible, so that we then get x by integrating up g dot g inverse. Okay. So now more about this add star. What exactly is this? Right, so if we say that V and W are in the vector fields and mu is a one-form density dual to the vector fields, then add star is defined by pairing it with W, integrating in L2, and what you integrate against is, add star means the dual, okay? So you integrate against this operator add, which is the commutator of vector fields in this familiar form, and then you integrate by parts, and now you're back to W, and this thing here is add star. So this is what that equation was telling us. Okay, so it has the usual type of fluid dynamics nonlinearity plus an additional thing. And ordinarily we may or may not worry about that, but this equation not restricted to Euler's equations for fluid. Right, this equation applies for any group and for any Lagrangian. So it's very flexible and it could be useful. But to make it, to go to the stochastic EP-diff equation, what we do is what I said, right? We have our let me go back. We have our this is interesting. Yeah, we have our reconstruction relation here, okay? So if we hit it from the right with G, then it's V composed with G. And if we make that into a stochastic process, we will add here some noise with this circle means Stratonovich noise. The Stratonovich noise has the property that you can do calculus with it. Everyone knows about Ito calculus for Ito noise. But Stratonovich has the property that you can not only do calculus with it, you can do variational calculus. So you can put it into Hamilton's principle. And what you need, though, to do that, is you need these amplitudes here, sigma, okay? These are the amplitudes of the noise, and these amplitudes are going to depend on where you are along the path. They're not just going to be some box of noise that comes in with just a coefficient, but they're going to be part of the solution. But you have to know something about them, and in fact that's going to be one of the interesting things, is about how does the solution you're interested in interact with noise? Because this is nonlinear, right? So our stochastic or EP-diff equation is now going to be given by the original thing we had, plus another add star with respect to this vector field acting on dl/dv, the same one, but now with this Stratonovich noise. Okay, and the thing which is interesting, a bonus that comes from having done it from this direction, is that this is a new type of noise. When I first derived this, I talked to my friend who's an expert in this, and I said, well, it's just multiplicative noise. And he said, no, it's not. Nobody does this. Nobody does it. Why? Okay, well, this part here multiplies the solution, but this multiplies the gradient of the solution. So when the noise gets bigger, the gradient gets bigger, the noise gets more important, right? So that's a feature that just the geometry hands it to you for free. Would you like this kind of new kind of noise? Okay. And then, because you did the geometry properly, right, you also have the benefits of the analysis that you did for the deterministic case will carry over as well. I'm not sure they always carry over.
Did you forget the noise on the right-hand side, or is it hidden somewhere?
Excuse me?
Did you forget the noise, that dw on the right, or is it hidden?
Oh yeah. Let's see. Oh yeah. I forgot putting the noise here. There should be a parentheses, right? Because that's just add star, and there's going to be the sum, and it's going to be summed over these guys. Yeah, I forgot the noise. It's just rewriting this term here, and this guy here. This is add star with respect to sigma on dl/dv, and that circle dw should be there. Thank you. Okay. Okay, so actually, more about the about changing the Lagrangian. I'm not going to go through all of this, but if you think about averaging, when you think about noise, right? You might think of some fluctuations being added to some Lagrangian trajectory, and if you average over it, it turns out you don't get what we're talking about here. You get instead a Lagrangian who is in H1 instead of L2, and whose variational derivative has this Helmholtz operator in it, and you define another momentum, because momentum is defined by dl dv, but if you take the average of this with the fluctuation, you get a different L, but you get the same EP diff, right? Because M is just dl dv, and out comes EP diff again. So that's like the Euler-Lagrange equations. Your generalized coordinate theorem. Whichever coordinates you choose, the Euler-Lagrange equations keep their form. Same with EP diff. Whatever Lagrangian you choose, it'll have the same form. And well, in some sense, that's why this is working, right? Because what we're doing when we, I guess I'll explain that later. Okay, so now we can do like Peter did this morning, okay, and express our velocity as integration against the Green's function, and we could take a Gaussian for shape analysis, or we could choose whatever Green's function we have. The H1 Green's function is here, and then we can represent the momentum, in terms of singular solutions. Okay, this is a sum of momenta and depend on time. We could make them depend on other Lagrangian variables too, and times the sum over delta functions. This is the map that Peter talked about. This is the thing which is called the singular momentum map, and the EP-diff has that. Okay, and these are the things which are called diffeons or singular solutions, but the point is it's a momentum map, and it doesn't matter what Lagrangian you're talking about. Because over here is dl dv, right? And this is always there because that's just the map. And it doesn't require any symmetry to have a momentum map. In fact, in this momentum map, you don't want symmetry because this is going to be the action of the diffeomorphisms on points in your manifold with positions q, right? Okay, and then this guy, now we substitute this into the EP-diff equation, and it turns out to be Hamiltonian. And this was guaranteed, actually, because that's what this map is about. It's taking you something from the cotangent bundle of a manifold into the dual of a vector space. In this case, the Hamiltonian transforms this way, so it is quadratic and times this Green's function, right? That we can choose whatever Hamiltonian we want too by choosing k. And we could change we could choose a k which has a whole bunch of bumps in it if we wanted. Okay, so then on optimization problems that we study are maps from some shape down to some other shape so that we minimize this Lagrangian thought of as a norm starting at some distribution of initial points and ending at some other initial points, final points. Okay, so now let's talk about stochastic landmark dynamics. We just talked about these landmark dynamics as these singular solutions. And to make them stochastic, what we do is we put in the motion that we had before, but in a stochastic form. So now we're going to add the stochasticity to the action of the Lie derivative on the manifold, the shape manifold with coordinates q, and we're going to constrain the variations. So the variations of q, so variation of p enforces this stochastic evolution, and the variation in q gives us the canonically conjugate evolution. And it gives it to us in terms of the new Hamiltonian for the change in the Hamiltonian is going to be pi dot sigma L summed over and times the noise. Okay, and this quantity here, pi dot sigma L q, is yet another momentum map. This is the momentum map for the infinitesimal transformations of the points q. Okay, well, under constrained by this p. So it's just p paired with the infinitesimal transformation, and it takes its value wherever we are on our manifold. Okay, so we can choose this transformation to be whatever we want. It doesn't have to be a symmetry. It's just the action on the manifold, which means you could say whatever manifold you like. You could have a frame bundle. You could have points on a real line. You could have intensities, and then for images, you could have all kinds of things that are possible data structures. Okay. So, let's compare this with stochastic force models. Usually, the stochasticity goes into the force, and also usually it's Ito. And in fact, with this particular forcing here, Trevet and Villard proved that, in fact, we have the good analytical properties as well, right? So you had existence and uniqueness, and I forgot the conditions for the solutions of the EPDIF equation. Okay, but this one's different for two reasons. First of all, it doesn't have this, it has this circle here. This is for Ito and this is for Stratanovich. And secondly, is Hamiltonian. Okay, so that you cannot make P move without making Q move, right, in a Hamiltonian system. And you can see this is d by dpi of h plus this momentum map. Okay, so that's actually a lesson, right, for us. How do we couple the motion to the noise? Momentum map. Okay, right? At the momentum map, this is we just looked at this, right? There's the momentum map there. Its derivative with respect to p gives back the sigma, and this derivative with respect to the q gives minus the derivative of this guy here, the distribution of the amplitude of the noise. Okay, and that's the momentum map, and that's how we couple noise to Hamiltonian systems. Okay, which momentum map is it? It's a momentum map that comes from the action of actually in this case, the Lie algebra on the manifold. So it's the infinitesimal transformation of the action of the group on the manifold, and then paired with P. Okay, that actually is this is the definition of the momentum map we need. That is the definition of the momentum map that takes us from the Q's and P's to the dual of the Lie algebra. Okay, and whatever you choose for your transformation, well, this is what we want to choose to couple to the noise. And the reason that we want to do that is because it's going to show up as a shift in the position, okay, of the path of whatever the group is acting on. When you drop it back down onto the manifold, this guy is going to produce shifts in the position. Here's the shift we have in mind, right? Usually this would be Well, this is the velocity, that's the drift of this process, and this is the noise. Okay, so it'll be drifting along in this direction and then have noise like that. Okay, so it'll look more or less like this. So first of all, the sigmas here, these amplitudes, in this picture, are they have a size which is twice the spacing. Okay, and the spacing is coarse, so you have low resolution. And what you're trying to do in this picture is to you're doing you're doing matching from this ellipse to the solid black line to that ellipse with the dotted line, and this is the comparison of the two types of noise. So the Ito noise is the magenta one, and the Lie transport noise is the blue one. Now the Ito one is constant, okay, but this Stochastic one is depending on sigmas that fall off like the K's do, away from the various points here. So you actually are seeing the interaction of the flow with the noise as it goes along. Okay, and the noise is different in this space than it is in between. Okay, because the noise depends on where you are. So here's how it looks if you raise. You go to higher resolution and raise the amplitude of the noise. You run it again. Okay, then you see more pronounced behavior in the blue ones, and the noise. This is the noise for the Ito, and this is the noise for the Stochastic. So these are not equivalent, remember, because the one for Stochastic has noise in both the Q and the P. Okay, so here's what it looks like if you go to high resolution but small amplitude noise with the high resolution means 200 landmarks. Okay, so there is a difference here between these two types of noise. Okay, now let's talk about metamorphosis. So, this is like one of those jokes, right? Horse walked into a bar. Lie group acts on a manifold. The manifold, okay, it contains the deformable objects that the group is going to act on, and the group's action is called deformation. So a metamorphosis is a pair of curves, depending on time, on the diffeomorphism group and on the space n, this manifold n, okay, which is parameterized by time, and at time t equals 0, on G is the identity. So the image of this curve is defined by the action of G on n, right? And now T depends on time. Okay, so this is the deformation part, and this is the template part, and right, if you don't give your template any time dependence, then it's more like fluid flow. Things just move along, and it's just a deformation. But in general, this image is going to be a combination of a deformation and dynamics on the template, right? It's also going to be changing, right? So, for example, the template may want to align with the direction of the flow, or align with something else, or take some orientation. Okay, so stochastic metamorphosis then looks like this. If there's no noise, then T sub T just moves along. And N sub T, the action just moves along under the action of the G. But if there is noise, then eta at time T gets mapped into this N of T, and for this realization labeled by omega, and it deviates from the deterministic case. And we can think about this as some kind of path of a landmark if we want, right? Because we saw that those landmark paths have that behavior. Okay, so we're going to study a variational problem. This is our setup now for metamorphosis. It's going to depend on the variables in the tangent space of G and the tangent space of N. Okay, we remember this definition and this initial condition. And suppose that this Lagrangian is invariant under the right action of G on the space G cross N like this. This was H is acting from the right, and it has this representation on coordinates in G and coordinates in N. Okay. So in this case, then we have we can transform to invariant variables the N new. So the point of having the left and right is just so that these guys are invariant, right? For any H. Okay, so now we have our reduced Lagrangian, and it's always a good trick. If you do have some symmetry, it's a really good trick to just transform to invariant variables, because the number of dimensions goes down, right? Okay. Now I have to, this is the last bit, there's some notation. So suppose G acts on this manifold N tilde. Then for an element of the dual of N tilde star, and an element of N tilde, then this operation diamond is defined by N tilde star diamond N paired with the vector field U is minus N tilde star, but now with U acting on N tilde. And these are two different norms, two different pairings. One pairing is on the Lie, with the Lie algebra of vector fields, the Lie algebra of vector fields and its dual, and the other pairing is on the tangent space of the N tilde with its dual, with cotangent space. Okay, so you can also think about U times N tilde. We're just denoting this as the Lie derivative of N tilde. So it's right. So the point is that the star is mapping N tilde star cross into N tilde into the dual of the Lie algebra, and that is a momentum map. Right. So star gives you momentum maps. Okay, the subscripts, we already explained the subscripts, they're on different pairings in different spaces. And now the notation for the star operation. This is Jonas's notation. I asked him why, and he said, well, you have the diamond. Okay, so if U acts on omega, which is dual, now this is this guy's on the tangent space of N tilde. If U acts on omega, and you pair it with something dual to it, let's see, in the dual space to it, then U star DLD omega DLD nu is the transpose of the Lie derivative acting on it. Okay, and Peter calls it the transpose. Right, Peter? Right. Well, it's different than the Lie derivative. Okay. So now let's compare the theorems for deterministic metamorphosis. These are the Euler-Poincar equations. See, they've got diamonds and stars in them. Okay, that came from introducing another whole space, and the space that's being acted on by the diffeomorphisms. And you can think of these guys here as this is like the velocity of the director in a liquid crystal, and this is the director itself in the liquid crystal. And there's still this add star. And the other feature is now that the momentum has been enhanced. It's dl du plus this guy here, and this guy is a momentum map, right? This guy's in the dual to this guy. That's the diamond. That's the momentum map. This is a transport. Okay, and we also have this auxiliary equation for how nu is related to n dot when you're moving along with u. Okay, so the point about this is that these equations, Euler-Poincar equations for this coadjoint motion, the add star means coadjoint, equivalent to this variational principle for this constrained action, and we've seen exactly this before, right? This is the velocity, the definition of the velocity in g. This is the definition of that velocity in the director in n. And now the Lagrangian depends not just on u, but also on n and nu. And the question is to make it stochastic, right? Because we'll have these equations. Now we want to make them stochastic. And the way to do it is in the Hamilton's principle, right? So change this to dg g inverse, make it a process, a stochastic process on the diffeomorphisms. And change this to u should be the drift now, and then we're going to have some noise, and the noise we're going to get by looking at the variability of the data that we're studying. Okay, if we have that, we have the sigmas, right? If we have that from the data, we can put it in here into the constraint, and when we take the variation with that constraint, then we're going to get the equation for the drift. That's the trick here. Okay, so this is what I said. The idea is to replace the deterministic evolution of these constraints in this Hamilton-Pontryagin principle for metamorphosis by introducing the stochastic process. Okay, and this is the first step, actually. Okay, the first step is to introduce the stochastic process on the diffeomorphisms. This is the velocity, right, corresponding to this. This is the part that drags in around, and later we can come back and add some stochasticity to that velocity too. But for now, let's take the first step. So D is the notation for stochastic evolution operator. Usually these things are thought of as integrals, okay? They're stochastic integrals. But to make things close to the usual dynamical systems or PDE language, this is what people do. You know, it's they do even actually much worse, but this is what we're doing. Okay, and so here's what happens to the equations. It's now this is the evolution of the same thing. It's still the total momentum, the part that goes with the LDU, in this part here, the momentum part. And this part here didn't change because it comes only from the Lagrangian. We didn't change the Lagrangian, we changed the constraints on the Lagrangian. Okay, so now we're taking variations. We take variation of u, and that's where is u? There's a u here, and there's a u there. And what happens when we do is we get this. So we didn't change the name or the properties of the thing which is evolving. We're just evolving it by a stochastic process. We change the vector field which evolves. See, everything where there's a dl, d something, it's the same as it was before because L didn't change, just the constraints. Okay, so the rub for all this, what's the difficulty about this? Actually is in the data, getting the C's, getting the noise vector fields. These things, you can think of these vector fields as the eigenvectors of a correlation tensor that you can measure assuming that you have some stationary statistics for a while. Or you can go all the way and do something more complicated, the time dependence. But just think of these guys here as something that came from data that is an eigenvector of your correlation tensor. Okay, and now the issue is to get the equations for u and, well, actually for dl du and for DLD nu. Okay, right. So this is what we're trying to get, and we've changed the equations for DLDU and DLD nu into stochastic processes. These are stochastic PDEs. Okay, so we had to put in. This is a decomposition, right, of the vector field. But for decomposition to make sense, you have to know at least one side of the decomposition, right? So if we know this, then we get the equations for this guy and this guy. Okay, so that's the rub. That's always the thing. There's a lot of data assimilation associated with this approach. And we've been working on this just for fluid equations at Imperial College for a year and a half, and we're just to the point that we understand that we can determine. We've just written a paper showing how we determine these C's. Once you have them, then you can run this equation again and again, and you get all these realizations. You'll get some then sense of the spread due to the stochastic bits. And what you next do, after you've got all this data, is you then do particle filtering on it to find the most likely paths through all this data. And that's going to be the answer for what is the uncertainty from this for this process. And the process we have in mind right now is just Euler's equation in 2 dimension, like the picture I showed you, and also so the idea is to do this for fluid dynamics that's geophysical fluid dynamics. So there's one for Euler's equation, there's one for a 2-layer quasi-geostrophic, and that's the first thing. We've got all the numerical runs now. We're going to take the high-resolution numerical runs as the truth, have low-resolution, coarse resolution numerical runs as what we want to model with the noise, and from the truth we get the C's, and then we run this and see how broad the errors are, and that's then the error in the coarse resolution. Okay, so if we now say let's couple our noise in a Hamiltonian sense, right? Then what we do is we want to now also, what I want to show you here is that the effect of this other part of the momentum map, right, which is affecting the evolution of the order parameter variables, the sigma and n for the metamorphosis, can be really important. Okay, so if we change our coupling from the momentum coming from the kinetic energy to this total momentum with this other momentum map in it, and we choose just the C's, then what happens when we ask what is the evolution of that motion, just the motion of the fluid, which we had earlier been computing? Well, what happens is that there's an interplay going on. This variation and that variation are talking to each other through the Hamiltonian structure. And an interesting thing, there's the coadjoint motion with respect to now the total, the drift and the noise acting on this part of the momentum map. And then there's another coadjoint motion acting on this guy. Okay, but down here, the stochasticity has canceled out. So there's going to be an interplay in metamorphosis between how you choose the stochasticity on the template and the stochasticity on the flow. So I chose to put them together, just to sum them together with the same noise, and then I found this cancellation. Okay, and if you didn't put them together with the same noise, then you'd get the difference between the two noises appearing here, which is going to be a big complication, I suppose. But it makes sense that the distribution of the noise for the template will be different from the distribution for the noise for the change of shape. Okay. But anyway, in either case, what I'm just trying to say is that the noise on the template variables is just as important as the noise on the flow variables. Okay, so here's some applications. This I said in the beginning, or maybe I meant to say in the beginning, that this is work with Alexis Arnaudin and Stefan Sommer. Okay, and this is some recent results comparing the various ways of using metamorphosis with imaging. You can use it for doing some population average. Okay, so you just want to find the average among a set of shapes. Okay, or you can use it for finding a trend by putting in some time evolution for how the template is changing. And this is just a type of regression. It's geometric regression, though. It's not linear regression. This is regression on a manifold. So it's a little bit, regression is kind of a weak word for what this actually is. And then you can also have this with the noise, and you see the indication is there's some kind of spread. And these guys we're going to have a bunch of these realizations and give some sense of the uncertainty, provided we have some sense of the C's, right, for the flow. Okay, thank you. I think that the EP-diff is a big bridge between images and fluid flows.
I always wonder, I know that analytically it's the right way to add noise, but I always wonder how, from a modeling viewpoint, using Stratonovich noise rather than Ito noise compare. Do you have an intuition? For me it's always, of course when you take the differential it goes away, but I always feel something weird about using something that will happen in the future to describe what's happening now.
But the thing that happens in the future actually is something like a Laplacian. Okay, because when you do the Ito correction, okay, but it's another bonus coming from the geometry. When you do the Ito correction for this type of noise, which has add star, the co-adjoint motion, has a Lie derivative in it. And when you do the Ito correction, you get a double Lie derivative, which depends on X's, and you're summing over all of them. And this is another new thing, is how to understand the drift, okay, which is caused by the equivalence between the Stratonovich and the Ito modeling, which comes in like a Laplacian in the Fokker-Planck equation, but it's not the Fokker-Planck equation. It is a double Lie derivative. If you do it for Hamiltonian systems, it's a double Poisson bracket, okay, which will dissipate something about your system. In general, it leaves you on a co-adjoint orbit, right? That's double Lie derivative. Leaves you on a co-adjoint orbit, but it dissipates the energy. Okay, the Fokker-Plancks that you calculate this if you're at low dimensions, like from the rigid body, will spread things out all over the angular momentum sphere, but leave it on the angular momentum sphere. Yeah. So I think that's a great question. Is what differences and implications are there, having gone to this type of geometric noise. I said it's a new kind of noise. It really is. And it'll be really interesting to see what happens with just the Ito correction. And it's the Ito correction that appears, this double Lie derivative or double Poisson bracket, has appeared before. And there has been a lot of work in the past by Jerry Marsden and Christian Prasad and quite a few other people, Tudorat, who also worked on this. It's like the geometric properties of the double bracket, or the double Lie derivative. The double bracket came in the, I think, 50s maybe 40s, in the work of Roger Brockett, who is a control theorist, and he found a way of finding good paths for mechanical systems with geometric meaning by imposing control with this double bracket. So it could be another whole story, because we're just following what the geometry tells us.
What about chaotic properties of the simulation you are looking at? For instance, in 2D for incompressible Euler, where you had noise, what kind of, have you tried to do this particle filtering problem? From the numerical point of view, or from the point of view of simulations, can you see some chaotic behavior? Or
yeah, sure. You saw, right, in that picture, all this folding and stretching, right? And you see the if you look at level sets of vorticity like this was, you see them turning and stretching and breaking, right? But and that's chaos in the sense of positive Lyapunov exponents, so that the paths are separating from each other. So there's a benefit and a difficulty with this. So you measure the time. Okay, you're interested in the decorrelation time, right? So you're interested in knowing that you've run this long enough to get the stationary statistics, and that it doesn't remember where it started. Oh, that's good from the viewpoint of positive Lyapunov exponents. On the other hand, if you run it too long, then everything is separated so far away, right? So how do we do that? Okay, so we're running like 20, 22 turnover times. That's a real long time for this sort of thing. And Dan Christen, who's leading the data assimilation part, is saying it's too long a time, right? Because exactly for the reason that the spread gets wider and wider, and it doesn't really help if you have included the truth in your spread, but your spread was all spread out by chaos. So the trick is at each time step for the coarse scale. Okay, so what you do is you take the velocity that you got from the previous step on the coarse scale, and you're comparing it with the step on the fine scale, and you multiply that by a random number. Okay, so you decorrelate between the time steps, on the coarse scale. Okay, you've got the fine scale, that's run for 20 turnover times, and you're comparing with that one. It has stationary statistics, and we look at the coarse scale at a certain time, and we say, how does this? And we choose a direction. Okay, when the noise is small. Okay, and we take the step, right? At each time step when the noise is small, and that way it doesn't spread out so much. So there's computational magic to be done in order to get something out of it. You can't let it spread out too much, or your particle filtering will take forever. You should come visit, talk to us. Well, can we send you a draft?
Sure. Welcome.
Thank you.
Because technical team want to finish for the file. So let's thank Professor Holm again.